Welcome to another video in our video series called Think 6, where we discuss interesting aspects of the next generation of wireless communication, aka 6G. In our last two videos, we learned the basics of machine learning and looked at one of the three use cases that are currently explored by 3GPP as a study item for Release 18. Today, we look even further into the future by exploring how this initial work may transform the air interface and in particular the physical layer for a future 6G standard. So welcome to part 3 in our mini-series on artificial intelligence and machine learning in future wireless communication, where we will take a first look on how an AI-native air interface for 6G might be realized. So the question is, what may change with 6G? Here you see a simplified block diagram of the common signal processing chain for the transmitter and the receiver, including the RF front end and antenna system. The characteristic of the wireless channel impacts the transmission and challenges the receiver to recover the signal correctly. In the past years, you find that academia and even key industry players began to explore replacing individual blocks in this chain with machine learning-based models. The next step is to combine blocks that logically belong together. For example, design and train a neural network that can perform channel estimation, equalization, and demapping. We would call that a neural receiver. The next massive step is to use machine learning to jointly optimize the entire chain for transmission, reception, and baseband processing. The ultimate goal of machine learning is to adapt the transmission to the environment, which means the underlying hardware, signal processing techniques, and application type. That implies that machine learning designs part of the physical layer itself. So, for example, the resulting waveform and constellation that cope with the channel characteristic, analog impairments induced by the transmitter and receiver components, and signal processing errors coming from the baseband processing. Those constellations may look much different from today's constellation diagrams of a QPSK or any of the QAM modulation. To do this end-to-end learning of a communication link, the concept of an autoencoder comes into play again. All of the above should trigger the question of when is all of this happening, and does it happen at all? Of course, it's hard to predict the future, and there's no chance to give any dates here, but from our analysis and current understanding, this may occur in three phases. Phase 1 focuses on the RF front end. Phase 2 focuses on the receiver aspects, and phase 3 for an end-to-end optimization, but given the associated challenges, has a big question mark at the moment. Let us discuss these phases a bit more in detail. We see phase 1 as very likely to happen. First papers on this subject using machine learning to model the non-linearities of the transmitter came out in 2020. Initially driven by universities, key industry players also published their findings towards the end of the year, suggesting that machine learning can outperform the classical methods to find, for example, digital pre-distortion models to linearize the power amplifier. The next step is to apply the concept to the entire front end, including the antenna system and transceiver part. For me, the most interesting part is that the later papers referenced earlier work and demonstrated additional improvements compared to the earlier findings, a clear indicator that the methodology has great potential. So you may ask why the optimization of the RF front end is an easy entry point for applied machine learning in wireless communication. The answer comes with access to datasets required to train the neural network. As the RF front end design is entirely in the vendor's hands, all necessary information is also at the vendor's disposal. Machine learning requires datasets to train the neural network, and I mean a lot of data. This data is not always easily accessible or even available to everyone who wants it. It provides one of the challenges for machine learning, particularly for wireless communication. So to understand why phase 2 may happen, we need first to know why there's room to apply machine learning for signal processing at the receiver side. If you are familiar with the 5G new radio standard, you know there's a zoo of reference signals designed to serve different purposes. The diagram spans the resource grid in time and frequency for a single resource block with 12 subcarriers on the y-axis and 14 OFDM symbols on the x-axis. The orange marked resource elements carry the demodulation reference signal sequence for the data channel. The receiver uses these pilot signals to perform least mean square channel estimation, equalizing all resource elements closest to the next pilot. For example, the information gained from the bottom left pilot signal in symbol number 2, subcarrier number 0, is used to equalize all resource elements within the purple rectangle. If we look at one area in more detail, we can conclude that the equalization process for the resource element closest to the pilot works pretty well. However, moving away from the pilot signal leads to equalization errors due to channel aging and imperfect channel estimation based on the deterministic compute algorithms. Various scientific papers demonstrate that machine learning can overcome these equalization errors and improve this mismatch. So the theoretical performance gains are quite significant. Here's an example from Nokia Bell Labs' work presented at the Artificial Intelligence Machine Learning for 5G Challenge organized by the International Telecommunication Union back in November 2020. If we compare the baseline, that's the pink curve, with the perfect channel knowledge curve, which is the orange one, and target a block error rate of 1%, we can estimate that there's a room for improvement of a little over 3 dB. Now with the neural receiver represented here by the blue curve, based on a fully conventional neural network that replaces channel estimation, equalization and demapping, we get very close to the perfect channel knowledge performance. So that shows that machine learning can outperform the traditional signal processing, in this case because it applies a data-aided channel estimation, equalization and demapping. But what is the ultimate step that researchers envision? It is to learn the communication link from an end-to-end perspective using, for example, an autoencoder approach. A potential result looks like this. It's coming from the same presentation. A trained constellation for specific channel profiles and Doppler spreads. The constellation looks way different than the traditional QAM modulations. It's not symmetric at all, which is required so that the receiver can synchronize to this adapted waveform. The additional performance gain comes from the fact that this learned constellation does not need any pilot or reference signals anymore. The freed up resource elements can now be used for data transmission and therefore contribute to another performance gain. With that, we have reached the end of our third video in our mini-series where we explore the role of artificial intelligence and machine learning in wireless communication, and we took a look on how an AI-native air interface for 6G may look like. Next is to evaluate what the potential impact on test and measurement solutions is. However, this is a topic for another video in our video series called Think 6, where we discuss interesting aspects of the next generation of wireless communication, aka 6G.